Welcome back, dear students, to this last video under Deadlock. In the previous video, we introduced Deadlock, we saw the different properties, and in the last video, we saw how to draw a resource allocation graph and how to determine if a deadlock will happen or occur in a particular scenario. We went through and we concluded with an exercise, and I hope before watching this video, most of you have already answered this question before having the solution in the WhatsApp channel during this weekend. Okay, today we are going to look at the different ways by which deadlock can be handled, methods of handling deadlock, and in general, there are four strategies of dealing with a deadlock problem. First of all, we have deadlock prevention, that is, prevent deadlock by resource scheduling so as to negate at least one of the four conditions. Remember that for a deadlock to occur, all the four conditions necessary for deadlock to occur must simultaneously hold. We have hold and wait, we have circular wait, we have no preemption, and we have mutual exclusion. So the first way deadlock prevention is by ensure that the resource scheduling algorithm we are using makes in such a way that one of the condition do not hold. Secondly, we have deadlock avoidance. That is, we avoid deadlock by carefully handle or schedule our resources. We have deadlock detection and recovery. That is, we detect whether deadlock will occur or not, and when it occurs, we take a step to recover from the situation in order to cancel the deadlock. And the fourth, which is the ostrich approach, that is, we just ignore the deadlock problem altogether. But this approach is not like too recommended as compared to the first three. Deadlock prevention. A deadlock may be prevented by denying any one of the conditions. One, which is we should eliminate the mutual exclusion condition. That is, this condition must hold for non-shareable resources so that many processes cannot simultaneously share a single resource. This condition is very difficult to eliminate. So deadlock prevention, for us to prevent deadlock, we need to eliminate one of the four conditions necessary for deadlock. And when it comes to mutual exclusion, we should make sure that the condition holds only for non-shareable resources. In such a way, many processes will not be able to simultaneously share a single resource, thereby avoiding this particular condition. The next one, we should eliminate the hold and wait condition. There are two possibilities for eliminating this particular condition. One is that a process request should be granted all of its resources it needs at once. That is, when a process is about to execute, all the resource it needs for its execution should be granted at once. Or secondly, we need to disallow a process from requesting resources whenever it has previously allocated resources. So in order to eliminate hold and wait, there are two possibilities. One, when a particular process requests for a resource, we need to allocate all the resources it needs in order to prevent the hold and wait. In such a way that what he will hold all the resources he needs and we will execute till termination. And secondly, we deny any request from a process which has been previously allocated resources. This strategy requires that all the resources the process will need must be requested at once. The system must grant resources on all or none. It is either we allocate to you all the resources you need or we don't allocate any of the resources. The third one, which is the elimination of the no preemption condition. This can be done. This can be done. This condition can be eliminated to ease by ease. There's a problem here. This can be done. This condition, this condition can be eased by forcing a process waiting for a resource that cannot immediately be allocated to relinquish all its currently held resources so that other processes may use them to finish. That's how we can eliminate no preemption condition. Force a process to wait for a resource that cannot immediately be allocated. That is why a particular process is waiting for a resource. We force him to be in the waiting state so that he will release all the resource it is holding for other processes to use them and execute the termination. Lastly, to eliminate the circular wait condition, to eliminate the circular wait can be denied by imposing a total ordering on all of the resource types and then forcing all processes to request the resources in order, that is increasing or decreasing. This strategy imposes a total ordering of all resources type and to require that each process requests resource in a numerical order of enumeration. With this rule, The resource allocation graph can never have a cycle, which is correct. That is, we make in such a way that what processes require the resources in a particular order, in such a way that when the first process on the line is being allocated all the different resources he needs, he executes and he terminates, then we move to the second one, and so on and so forth. By so saying, we can never have a circular wait. And if there is no circular wait, it means that no matter the three conditions holding or not, we cannot have a deadlock. Coming now to deadlock avoidance. This approach to the deadlock problem anticipates deadlock before it actually occurs. That's why we say deadlock avoidance. In deadlock prevention, it means that what we make in such a way that we prevent that, we make everything possible in order not to have the deadlock. But in deadlock avoidance, we anticipate in such a way, in other words, we can have deadlock here, but we make in such a way that we do not arrive at that particular state. It employs an algorithm to access the possibility that deadlock could occur and acting accordingly. If the necessary conditions for a deadlock are in place, it is still possible to avoid deadlock by being careful when resources are allocated. It employs the most famous deadlock avoidance algorithm, that is the banker's algorithm. For this our level, we cannot dive right into the banker's algorithm, but you need to know that this is the most famous algorithm we use for deadlock avoidance. Coming now to deadlock detection and recovery. If a system does not employ a deadlock prevention or a deadlock avoidance algorithm, then a deadlock situation may occur. In this case, the system must provide an algorithm that examines the state of the system to determine whether a deadlock has occurred, an algorithm to recover from the deadlock. That's what we say deadlock detection and recovery. According to number of instances in each resource type, the deadlock detection algorithm can be classified into two categories: single instance of each resource type and several instances of a resource type, because we know that a resource can have one instance or several instances. When a detection algorithm determines that a deadlock exists, the system or operator is responsible for handling deadlock problem. There are two options for breaking a deadlock. One, process termination. By aborting all deadlock processes or aborting one process at a time until the deadlock cycle is eliminated. That's one of the way of breaking a deadlock. Two, a resource preemption, by either selecting a victim, and a victim here is a resource and process to be preempted based on a cost factor. We have holdback and we have starvation. That is, the system or operator should ensure that resources will not always be preempted from the same process. So, guys, these are just the different ways by which deadlock can be handled, either through detection to avoid, either through detection and recovery, through avoidance, or through prevention. I hope you enjoyed this video. Do not forget to like, to subscribe, and to share for our community to grow. In the next video, we can talk about some different terms which are associated with process scheduling, such as convoy effect, starvation, and we shall also go further into process synchronization. Thank you for listening, and I hope you learn a lot. See you in the next video.